Good afternoon, everyone. First, thanks for the introduction, and I appreciate the invitation from organizer and IPAM. Today, this morning, Dr. Arisa talked about the continuum models for monolayer and bilayer system, and now I'm going to talk about different continuum model for monolayered system. And this talk mainly focuses on mathematics and analysis. And unfortunately, we don't have some very interesting physical phenomena to present, but we try to make our model as rigorous as possible. And I also want to thank my collaborators, Julian from Warwick and Derek Olson from RPI. Okay. So here's the outline of my talk. I will first talk about the motivation, non-flat configurations, or the ground state of 2D materials, basically ripples, wrinkles, and crumples, and etc. And then we would like to use Von-Karman plate theory to model this 2D material and non-flat configurations. We will give some minimal assumptions on this empirical atomic potential, and we will rigorously prove what's the correct scaling rules to study the convergence of Von-Karman, to study the convergence of this Von-Karman approximation. And then we will introduce some appropriate norm that reflects the observed stability, mainly to maintain the out-of-plane displacement being stable in the system. After I talk about the continuum model, I will show you some stability and error analysis in terms of linear stability, force consistency, and displacement field. And I will also talk about some issues we have right now and some ongoing work which is related to multiscale modeling. And then I will give you a short summary. So first, motivation. So graphene is locally two-dimensional, but it's not flat. And in our recent paper by Stefanelli and his collaborators, they rigorously proved that the graphene under the condition of suspension, the only two possible ground state is either rippling or rolling up like a crumples. And based on the kind of geometry atomic potential you are using, then you will get either ripples or some crumple configuration for the ground state of graphene. And since this work is from an atomic point of view, so we would like to see if we can derive some continuum approximation that be consistent with their result. And our interest is focusing on ripples. And for ripples, in this 2016 review paper, these physicists and the engineers, they simulate and summarize the formulation properties of ripples, crumples, and wrinkles. And they point out that for ripples, each ripple is kind of like an isotropic valley or peak, and the height is about, it's about maybe 100 sides compared to the lattice constant of graphene. And each valley is reasonably, I should say it's not very large. So in other words, the ripples are kind of like with a small energy perturbation compared to a flat graphene. And we would like to take this into account when we model the continuum approximation. And there are quite a lot continuum models proposed in the last 20 years. And for example, you can use similar ideas like about Cauchy-Born rule to model graphing. For example, you can introduce this exponential geometry map and then locally map each tangent field into a curved space and then propose the continual approximation for this curved space. That's the exponential Cauchy-Born rule. You can find a reference paper from Belashko 2005 or maybe 2003. But this exponential CB rule, from my point of view, mainly targets for model nanotube, or you can think of rolling up configuration rather than this ripple configuration. Another type of high-order Cauchy-Born rule is, for example, you can find some so-called local Cauchy-Born rule from Wei-Nan Yi and Jerry Young's 2006 paper. So it's similar to this exponential Cauchy-Born rule, but instead of introduce the exponential map to map the flat tangent space to curve the tangent space, they use high order, say, first derivative, second derivative, and etc. high order derivatives of displacement field to reconstruct this curved configuration, and then plug the reconstruct configuration into the environment of atomic representative atom, and then they got the local Cauchy-Born rule. And in 2018, actually this paper submitted in 2016, Paul and Mitch has developed some Cauchy-Born rule for incommensurate bilayer system. And so to the best of my knowledge, most methods developed here are not aiming for ripples. And the second type of approximation techniques is one can use harmonic approach. So for example, this morning, Dr. Risa introduced how to iteratively adding force corrections and then approximate the interaction energy. Or you can also apply discrete Fourier transform and derive the discrete lattice green function. And in this 2008 paper, they proved that the far field decay of discrete lattice green function behaves like a linear Kirchhoff plate for graphing. And in recent manuscript by Xingjie Li and his student Xiaojie Wu, they actually apply this idea and they simulate the monolayer graphing with stone wheel defects, and they capture this cosine configuration. And this Cauchy-Born rule is nonlinear model. By harmonic approach, basically give you linear model. And there are other nonlinear models, for example, using Von-Karman plate theory. So quite a lot of engineers have applied this Von-Karman plate theory to graphing. And I want to point out, for example, in this 2014 paper, Dr. Jianhua Gao and his student and other collaborators, they actually used this generalized Von-Karman plate model and model ripples and winkles. And because for our goal is try to derive a rigorous continuum model from ripples. So based on this consideration, we want to focus on Von-Karman. And we searched the literatures, and we further found, Von-Karman plate theory has been successful for many applications. For example, in 2015, Kuma and Vivek Chenoy's paper, they use Von-Karman to capture Moiré pattern and ripples for bilayer system. And Jianhua Gao and his collaborators use this generalized Von-Karman plate to training topological defects and the configurations of graphene. So based on this success for applications from engineers community, this built us confidence. Okay, the Von-Karman plate theory might be a good approximation model. And what's more, one of my collaborator, Julian, his thesis is about develop a Von-Karman theory for multi-layered graphene system. But in his work, I think he does not specify the van der Waals interlayer interaction. But nevertheless, we can still borrow some proof techniques from this paper. And also, we found a very interesting review paper, 2016. This paper rigorously proved different scaling laws of continuum plate will lead to different plate model. So, for example, if the external force or the total energy scaled as h squared, where h denotes for the thickness of the plate, then you get the linear Kirchhoff. And if it's scaled as h force, we will get Von-Karman. So this is very important. So because based on this continuous theory, it gave us some idea how to propose minimal assumptions on the continuum energy, on the atomic energy, and then how to scale everything properly to get a continuum model. So our goal is to derive the continuum Von-Karman and also provide a rigorous analysis. So let's think of simple lattice, though the graphene is multi-lattice, but for the purpose of simplicity, let's only look at simple lattice at this moment. And the lattice, the configuration is deformed one-dimensional higher. And we developed a theory for both 1D and 2D, but to explain the idea, let's focus on 1D. And we assume the lattice constant and the number of atoms give us 1, which means the microscopic domain is fixed from 0 to 1. And then we compute we denote the displacement field by U1 and U2. So these U1 and U2, they are physical displacement. So you can imagine that the magnitude of these two will rely on the magnitude of lattice spacing. And for the 3D bulk materials, U1 and U2 scale the same way. But for 2D materials, like observed in the experiments, the U2 part scales has magnitude bigger than the U1, or the out of plane displacement is bigger than the in-plane displacement. So this suggests we need different scaling rules for U1 and U2. And because we want to we compare the continuous theory, and then we proposed minimal assumptions on the atomic potential. We assume this atomic potential contains two parts: the pair interaction up to nearest neighbor, and three-body potential, such like angular potential. And the pair part is just like a quadratic or the harmonic potential. And the three-body part also behaves like quadratic. And we assume that the total atomic energy scales like C times epsilon to the fourth. And then we can find a recovery sequence basically is close to the rigid motion. And follow this recovery sequence, we can prove that the atomic energy is converging to this guy. And we can also specify the scaling rules for in-plane displacement and out-of-plane displacement. So they are different. So the in-plane is one order higher compared to the out-of-plane. And so we have the atomic and continuum model, and the gamma convergence only tells us they converge into this guy, but does not tell us the convergence rate. So for this purpose, we introduce some analysis tools. For example, first order difference operator, which approximate first derivative, and a second difference operator approximate the second derivative. And then for physical unskilled displacement, we define the semi-norm looks like this. Okay, because the in-plane and the out-of-plane displacement, they scale in different way. So we have to add this epsilon squared in order to have the convergence to the continuous norm. Okay, so based on linear or Taylor expansion, we can prove that this atomic model is stable with respect to the atomic norm, and the continuum model is also stable compared to the continuum norm. And if you compare the stability constant, they are very close, except the continuum model is slightly more stable. I'm not quite sure, but so far this result is consistent with the bulk case. In the 3D solid materials, we do have Cauchy-Bonne is slightly more stable compared to atomic, and their lattice stability constant are similar. And then we applied tedious Taylor expansion to both pair interaction and the angular interaction. We can get that the continual total energy is second order consistent comparing to the scaled atomic energy. And based on this, we can further compute the atomic forces and then compare with the scaled continual forces. We find that the order the difference is of first order. And then combine the stability with force consistency together, we can prove the continual displacement field is of first order. Okay, that's for 1D. And similarly, we can extend to 2D. So again, we need the 2D total atomic energy should scale like epsilon to the fourth, where epsilon is the lattice constant. And this time, the minimal requirement for atomic energy should include 3 parts. So up to 4-body interaction, this G omega. And then the displacement field, again, scaled differently for in-plane and out-of-plane. And follow the same analysis and the recovery sequence, we can get the continual Von-Karman total energy. And so again, the 2D case have similar results compared to 1D, second order in terms of energy difference, first order in terms of force, and the first order in terms of displacement. And I also want to point out that we need 4-body interactions, but on the other hand, this requirement is not very restricted. At least Tursoff and Brenner type interaction potential satisfies these assumptions. So that means the assumptions we propose for 2D are reasonable. And then yesterday I tried to simulate some 1D model, but I feel maybe because I have some bug in the code or because we are not very clear about boundary conditions. So actually, the boundary conditions turns out to be more sophisticated than we were thinking. So for example, in 1D, in Stefanelli's paper, they figure out that in order to get ripple or crumples, you have to specify the length of E1 direction. And this mu is within a subset of 2/3 to 1. And with different value of mu and different choices of atomic energy, you will either obtain a ripple with a simple period or with some complicated ripples with several different periodicity or even crumples. So that's for 1D. For 2D, to the best of my knowledge, so Jianhua Gao and his students, they apply these crumped boundary conditions to E3, and within plane, they slightly shrink the domain or apply some string conditions to the in-plane, and they obtain the ripples and the winkles. Yeah, and another interesting extension for us is to, once we are clear about the continuum model, we want to develop an A2C model, and we need to specify the size of blending region. This part will be tedious, but similar to a lot of existing A2C work. And finally, let me give you a short summary. We derived the continual Von-Karman model from atomic description, and we want to emphasize that the scaling laws played is very important, and we rigorously proved the error in terms of energy, force, and the displacement field. We are not clear about the boundary conditions for the continuum model, and we also want to extend the continuum model and develop the A2C multiscale model. Yeah, thank you.